Conservation of energy. Our purpose today is to use conservation of energy to find the spring constant of a rubber band. The relevance, we're practicing the use of this thing called conservation of energy. Success, I'll be able to create the proper equation for a situation and then solve for an unknown variable. So for every story problem on your homeworks and on your quizzes and tests, you'll have to figure out exactly how you arrange the conservation equation, what goes on the left and what goes on the right. So we have a little bit of homework here tonight, and the quiz is going to be most likely after Thanksgiving break, I guess. I might try to squeeze it in. No, I'm not going to squeeze it in.
Thank you.
Here we go, warm-ups. What blank of energy equation says initial equals final? What's the word that goes in there, do you think? Conservation. Conservation of energy says that whatever we start off with, we have to end up with. Circle the equation for elastic potential energy.
The second one. The middle one.
The little k here stands for kinetic, the energy of motion. We have a velocity to go along with that. The little g here stands for gravity, and we have things falling a certain height. So the h tells us the height of the fall, so that's for gravity. Here we have a little tiny e that stands for elastic, and the x stands for how far it gets stretched. Number 3, circle the equation for gravitational potential energy.
That was the middle one, for sure. 100%.
That's the one, little g for gravitational.
That's what we're talking about.
Okay, now in our elastic potential energy, what does the K stand for?
Look at the history. No idea.
It's something called the spring constant. It's basically how easy it is to stretch. Actually, the higher the number, the harder it is to stretch. The X, it stands for the amount of stretch. You can also compress things and get the same equation. Number 5, a spring has a spring constant of 5 newtons per meter. Now that means that for every meter that you stretch it, you have to exert a 5 Newton force. Okay, it is stretched 0.2 meters. What is the spring's elastic potential energy? So we write down this equation. E with a sub E is equal to 1/2 kx squared. We are looking for the energy. So the E stays a letter. We're going to put in numbers for everything else. 1/2 comes down. The K is our 5. The X is the amount of stretch, 0.2, and we've got to square that. Typing this in, 0.5 for 1/2 times 5 times 0.2, and I got to square that, and I get 0.1. 0.1 joules. Number 6, a rubber band is stretched 0.1 meters. It stores 6 joules of elastic potential energy. What is the spring constant? Okay, we're still dealing with elastic energy, so we have big E sub E and 1/2 kx squared. But we're looking for a different variable this time. We are looking for the spring constant K, so that stays a letter. We put in numbers for the other things. The capital E is energy, and we're told that that is 6 joules. Bring down the 1/2, and the X is the amount of stretch, which is 0.1, and we're going to square that. On my calculator, we're not going to do calculator yet. Let's simplify this a little bit. We have 0.1 squared. Okay, let's do that part. 0.1 squared, we get 0.01, and then multiply that times a half. 0.005. And then we have to multiply that times the k. I'm going to transfer this over up here. So I divide both sides by what? Do I divide by 6 or do I divide by that 5 thing?
The 5 thing.
By the 5 thing. So 6. Do I expect a big number or a little number?
Yes, it's 1200.
Big number, 1200. You're dividing 6 by a teeny tiny amount. You're dividing up that 6 into tiny little piles. You gotta have lots and lots of piles, 1,200 of them. Number 7. The rubber band in the previous problem is shot straight upwards. Use conservation of energy to find out how high it flies. So, the initial energy is equal to the final energy. The initial energy is elastic. It's the stretched rubber band. The final energy is going to be gravitational. How high up? How high could it now fall downwards? So, the E on the left-hand side is elastic. That's 1/2 kx squared. The gravitational on the right-hand side is mgh. We want to find out how high it flies, which is h. Got to put in numbers for everything else. So the g is going to be 9.8. It's always the positive version of 9.8. The mass, oh my goodness, do I have a mass written down here?
No.
Drat, I forgot to include a mass. So Davis, make up a mass that's appropriate for a rubber band.
0.19.
Okay.
You make one up.
0.019.
Yeah.
That's a hefty rubber band. That's okay. That's in kilograms now. 19 grams. So think about one of the biggest rubber bands that you have seen. And that'd be one of these. And that's about right. Hello, TSI is here for somebody.
Andrew? Your name right?
On the left-hand side, X is the amount of stretch. We're told that it's stretched 0.1 meters. And we got to square that. And the K value we just figured out to be 1,200. And then we have the 1/2 in front. On the right-hand side, let's multiply all that out. 0.5 times 1,200 times 0.1 squared. That's 6. And that's what we were told originally. On the other side, 0.019 times 9.8. Whoop, I did that wrong. 0.019 times 9.8 equals 0.1862H. Divide both sides by that decimal, and we get 32.2 meters. Solve for K. So here's some sample math that you might end up by when you're doing these kinds of problems. We have an elastic energy over here, and this looks like it's gravitational energy. So let's just practice our math here a little bit. Go ahead and do that on your own, and when you're done, check on the screen. Any questions on that? On the next page, Finger Rocket Lab. You will work on that. The Schoology page has the analysis questions of that. So it asks you for the different measurements, asks you for the mass in grams. The second question asks you for the mass in kilograms, and so on. So go ahead and answer all these questions first on paper, and then go on to Schoology and respond to those. There is a homework assignment on Schoology as well. Please rip off the wrap-up sheet at this time and put it underneath your desk on the book rack. That way, in the last couple minutes, when I call for wrap-ups, you know exactly where they are, and they're not stuck away in your backpack at all. Please remember to turn these in as you walk out, and don't give them to another student in order to have them turn it in. The way that I can quickly determine that everybody hands it in with lots of ease on my old brain is for you to hand it in to me, each person, as they walk out.